So welcome to the Local Highway Technical Assistance Council's GRS-IBS construction workshop. We're happy that you guys are all here with us today. I just wanted to let you know that we are going to record today's session and we'll send the link out to everybody in attendance today, and feel free to share those with those in your agency that missed today's training. Today, what we're going to cover, kind of an introduction of who's going to speak today. We're going to talk about local Idaho bridge needs, GRS-IBS overview, the planning and design process, construction, and examples of real-life projects that have recently been completed. Today, on our presenter list, we'll have myself, Don Christensen. I'm with LHTAC. I'm the communications officer. We'll have Matthew Seifus, who's LHTAC's GIS and database analyst. Scott Wood is our federal aid design engineer, Amanda Lamott, our TAP engineer, and we have got Matt Hall with HMH Engineering, who's going to cover some of the construction information today. We've already talked about the Zoom key features. If at any time you guys are having trouble, feel free to message me in that chat box. All right, so next on our presenter list is we're going to have Matthew Seifus talk a little bit about LHTAC's bridge maps and the tools that we have available.
All right, to access our online bridge maps from our homepage, just click on resources. And once that pops up, you can scroll down to the map section where we have our interactive bridge map. And it'll show all the bridges initially, and you're gonna wanna start in the upper left-hand corner. You may be familiar with this already. If you're looking just for the bridges for your jurisdiction, you're going to want the local road jurisdiction section here. County refers to all the bridges within a county, regardless of jurisdiction. That was a request we had, so that option in there. So, as a demonstration, we'll click on this one, and I'm just going to choose Bingham County because I know they've got a lot of bridges, and that'll jump you straight to their area here. And from this selection, you're able to automatically choose a set of bridges, and you see the information populates down below. And if what you're looking for is not among these attributes, there are quite a few more, which I don't show initially because it would really clutter things up. But for instance, if you're looking for details on the last bridge rating, first of all, clicking any one of these headers will sort based on that header. But you see this little arrow on the right. If you click that, besides the sort options, you have columns. And that'll give you all the other attributes that are available. So if you want to see the other ratings here, you can see them all listed, and you simply check one, and it'll pop in to the list here. So that's one option. Also, if you see a bridge you want more information on, you can click it and you see that it highlights in pink. You can then zoom in, and it gives you options. Over here you can change to see a different background, which might give you a little more information as far as what the bridge actually looks like. And in your, let's see. So if, let's jump back here. Make this a little bit easier. So in your selection, let's say you don't want to draw a box because your box is going to pick up a whole bunch of bridges you're not interested in. Do one of these. And that's like just the bridges you want. And just, so now let's clear this. Then if you jump into these bridge filters, that gives you some additional options to narrow down your choices. As an example, we're gonna get all the bridges that cross over Peoples Canal. You can see now what we're left with. This is everything for Peoples Canal. And from here, once I select some that I'm interested in. I have some options. You can see in the statistics area here, I can actually download, this will download a spreadsheet, anything in blue. On this map, if it's selected or highlighted, those are not downloadable on this map. I'll show you later on a separate map where that actually is a possibility. And let's see. And the spreadsheet download that you'll see, we'll just do one really quick here. So this is the spreadsheet that it will download for you, and you'll see actually all the attributes regardless of how many you have selected to view in the web browser. This will actually pull all of them, and then you can delete or rearrange as you want in your spreadsheet. But it includes a latitude, longitude, so you're actually able to map all of these. And that's that about covers the basics of the web mapping. Some of you are probably already familiar with that. Are there any questions or things that I can help you with here?
So we had 2 people jump on kind of while we were introducing that. So I just want to make sure that they know we went on the LHTAC website and we went to our resources page and found the bridge mapping tool, and that's what Matthew has been showcasing. All right, so if we don't have any questions, we'll jump back. And next, I'm gonna pass the mic over to Amanda Labat, our TAP engineer here at LHTAC, where she's gonna talk about our small structure inventory.
Good morning, everyone. I presented a similar slide to this at our workshops, if any of you attended our workshops last fall. The 10-foot bridges are also shown on here. Oh, Scott, is that a question for Matthew, in the bridge map? I saw a question pop up. Are the 10-foot long bridges also shown?
The 10-foot bridges are not shown in that map. Eventually, there is a plan to combine it all into one, but we have a separate map that shows the 10 to 20-foot bridges or small structures that we've been collecting. That is a work in progress. And that has a slightly different look. It has a newer framework and a couple of other features, and we'll be demoing that one a little bit later in the presentation.
Okay, thank you for answering that question. So we have been tracking the 20-foot bridges and longer for quite a long time. Those are all the ones that are required to be inspected every year, or whatever the recurrence that is required based on their condition. So what ITD was reporting is they report all of their bridges that are 20 feet and longer and 10 feet and longer. However, LHTAC only had data on our 20-foot and longer structures. So we wanted to get a better representation of how many structures, whether that's 10-foot and longer or 20-foot and longer, so we can compare apples to apples. So last year we had a big push, and we actually gathered that number. 20-foot and longer, we still have more than ITD. We have 2,427 locally owned bridges compared to 1,365 on the state system. But the big question was how many structures between 10 and 20 feet. And so that 1832 is that magic number that we were looking for. ITD has about 492 structures, and with all of your help, plus a lot of LHTAC staff going out to many of your local jurisdictions across the state, we counted up to 1832. And the interesting number is 69% of the total bridges are on the local system, and that is 10 feet and longer. So that's a huge number. You know, we wanted to make sure to capture that 1,800 structures to help get a better picture of that. We are still looking for help on that information. If you go to the next slide, we sent out information to all of the local jurisdictions with that information. So many of you didn't have that data and didn't know how many bridges were 10 feet or longer in your area. So after we collected it all, we were able to send out a map and a spreadsheet to give you that data so you can start keeping track of that. And maybe you didn't even know those bridges were there, or culverts or CMPs. So with this information, it'll help you do a better job managing your inventory and just watching the condition, because the structures 10 feet to 20 feet do not get inspected by ITD. So this is to help you. It's got the latitude and longitude. Like Matthew said, we are working, I think we already have a map developed and it's on our website that shows just the 10 foot to 20 foot structures. So this is just some more data to have in your back pocket as you're managing your inventory. And as we speak to ITD and legislators on funding, you know, this is a really important piece of the conversation so that we are capturing the total bridge need, not just bridges 20 feet and over.
So at this time, I was going to say, at this time, we're gonna bounce it back to Matthew so that he can pull up that small bridge map for us as well.
All right, so back here on the LTAC's website on the resources page, under the map section, we also have the small structure map. So this includes bridges, culverts, sometimes tunnels or underpasses that are 10 to 20 feet. There are a couple of bridges in here that are simply not in the state system for some reason, so they are actually over 20 feet, but that's only a small handful. Once we pull it up and you open up this left panel here, this will show you the layers currently on the map, and this little funnel is where you probably want to start. This will take you to your area filters. So this is similar to what you saw before in the bridge map. So in here, the county will show you all the bridges within a county, regardless of what jurisdiction actually is over them. But we've divided this so the cities for city jurisdiction, or whether they have jurisdiction or not, and then the rural road jurisdiction. So this will be your county road and bridge or your highway districts. So we will try, let's go here to Bonner. So we jump up to Bonner. These are the 10 to 20 foot structures within Bonner County. Same idea, you can select with a box or you can draw with a shape if that meets your need better. In this, let's see, so if we want to filter more, we can go to the next icon over, which is our bridge filters. So we're going to do a similar option here where we're looking for Kokolala. So now we see what's going over Kokolala Creek. And in here, once again, if you select in the table down below, it will highlight in the map up above. And you have same options here where you can sort by the different columns. This is all the information that's available currently, is the attributes that are shown, unlike on the bridge map where you had quite a few additional columns of data you could add in. But when you go to this third section here, the statistics, you have additional download options. So besides a spreadsheet, you can also download in a GIS format, which several people were asking for. So we've added that in here. And once again, you can click on any one of these blue items to download those structures in the format that you have selected. And in this, the small structure map, it does actually allow you to download only those that you've selected or the ones that are highlighted, if that's what you would prefer. So overall, it's similar. You do have a couple of extra features in here. You can search on, for instance, an address, and it will jump to that place and allow you to see what's around that address. And this, some other navigation options here. I'll let you explore those. But you can also create a PDF of what you're viewing. That was another request that we had frequently. So you can take a snapshot and put it in a document, or just create a PDF if you'd like to. And then some of the other things, I'll let you explore those, but those are the options that we have in our small structures map. Anyone have a question there?
Thank you, Matthew.
Yes.
Thank you. So we're going to pass the mic back over to Amanda, and she's going to talk about some bridge prioritization.
Yeah, we're just gonna, while we have you, before we start talking about GRS-IBS, kind of highlight some of the things that we can do to help you in determining whether GRS-IBS might be a good fit. So one of the questions we get a lot is, which bridges should I repair and which bridges should be replaced? And you can always call us if you have questions or if you need help answering this question. We have been helping several jurisdictions a year that reach out to us and ask us, like, which ones do I put in an application for? And we always start with the inspection report. Look at I circled it down there. Look at your condition ratings. Are they 5 or above? And if you look at that chart, that means is it in fair condition or better? If it is, then it might be a good candidate for rehab or repair instead of full-on replacement. You know, and then take a look, is this bridge on a priority road or is it serving one house? You know, it makes a big difference whether it's servicing lots of logging or farms or dairies or beet dumps, you know, whatever it is, that has an impact on whether your jurisdiction is willing to invest the money to repair or replace that bridge. And again, if you need help, please reach out to us. We will customize whatever you need based on what you're looking for. And if you need help finding a copy of your inspection reports, those do get mailed to you, but if you want any of those, we can always email them to you. So how can we help? If you reach out to us, we work with you to figure out what your priority routes are, how much money do you have to spend on bridge maintenance, and then we work with that information in mind, work with ITD Bridge Asset Management to see, because ultimately they're going to be the ones to either reduce or remove the load postings. We want to make sure that ITD is on board with any of the changes that we make or recommend. So we work with ITD to figure out what are some good low cost, medium cost, high cost solutions to either repair your structure or rehab. And then if that isn't ideal, then we'll let you know that this is a bridge that you want to reach out and put in an application for replacement. And then if you want us to come out and present the information to your local jurisdiction, whether that's your city council, your commissioners, you know, many of you are road and bridge supervisors, but you ultimately don't make the decision on what structures get applied for or where the money goes. If you want us to help you make a case, then we will come out to your jurisdiction and present that information. So one example, if we go over, we worked with Washington County last year. They asked us to help them look at 7 of their structures that were load posted. It was all their load posted structures. We worked with ITD and came out to their local jurisdiction and made a presentation, and their commissioners were thrilled that for less than $50,000, they were able to remove the load posting for 5 of the 7 structures. And 2 of those, we said, you know what, repair and rehab is maybe not the best idea, you gotta replace it, but $50,000 is a lot easier to swallow, and it makes them look really good. It keeps their bridges in good shape, keeps commerce flowing. So that was a big deal. And one of the examples I'm gonna show in the next slide is what we would present. So this structure is in good shape. You can see the condition ratings for the deck was a 6, the superstructure was a 7, and the substructure was a 7. Those are pretty good numbers, and overall the bridge was in good shape, but it was on the verge of increasing load posting because the girders just were not designed to handle the weight of the trucks driving over it. So our suggestion to the jurisdiction was to strengthen it. And if we presented these pictures, and then the next slide shows that we gave some long-term and some short-term recommendations. The short-term one came right from their inspection report. When the ITD inspector goes out to their bridge, they always have comments on things that they notice on what needs to be repaired or replaced. So that came right from the inspection report. The long-term improvements were recommendations made that said, instead of replacing this bridge, how about you add some C channels to stiffen the girder and increase the capacity. ITD and LHTAC can't do the design for you, but we can help you connect with engineering resources who can do that design. And at the end of the day, it's a solution that the jurisdiction can do with their own labor. They just have the materials delivered, and they were going to pursue that solution in order to keep their bridge handling the types of trucks that wanted to drive over it. So this was a good example of, we don't need to replace this bridge. It's in good shape. It'll last a long time, but for a $20,000 investment, it will service what you need it to.
So that's a good stopping point for some questions. If anybody has any for Amanda kind of on that process and what LTAC can do as far as bridge preservation and inventory and assessments with.
I did throw a note in the chat that the LTAC bridge map does have the bridge condition and the last inspection date, along with a lot of those individual rating scores. But for the full report, you can contact ITD.
Yep.
So,
Or us.
So next we're gonna just launch a poll. How many local bridges are in Idaho? So we're gonna launch that one next and see. We're talking about local bridges. At this point, we're talking about those 20-foot and over structures. So 2427 is our magic number as of August 2020 data captures. That's how many local bridges we've got. So next, how many of those 2427 local bridges are older than 50 years? How many of these bridges out here are older than 50? We're gonna launch that one next. So 893 is what our data captured for August of 2020. And these numbers are always changing.
Yeah, that kind of leads into this. So this is why we're here today. You know, we're looking for ways to help that number go down. You know, we have 2427. I think everyone got that number right or pretty close. That's the number of bridges we have. The scariest number is that 893. Those are the bridges that are over 50 years old, and that number is climbing faster than the number we are replacing. So we replace, I don't know if there's a click, if there was an animation, but I thought there was a line at the bottom that says we replace about 10 to 14 bridges a year. Oh, it's on the next one. So we replace 2 to 4 bridges a year with LTAC funds, and about 10 bridges get replaced a year with your own local funds. So we're only replacing that number every year, and every year we add way more than that to the list that are over 50 years. The hardest part about that is our funding has stayed flat the last 5 years, and it's projected to stay flat for the next 5 years. We only have about $7.6 million to replace bridges a year through LTAC, after we take $1.9 million about for bridge inspection and load rating. We only pay for what we actually spend on bridge inspection. So if a bridge is in good shape, it only needs to be inspected once every 4 years. If it's new and less than probably 20 years old, the older it gets and the worse the condition gets, the shorter that time amount is. So it can go to 2 years and to 1 year and 6 months. We have some bridges on our system that need to get inspected every 6 months. And the older and the worse condition things are, the more inspection it needs, and the higher the cost is to pay for that inspection. So we still have the same amount every year, but if the cost to inspect it and load rating continue to increase, then it just reduces the amount of money we have. So only 7.6 million. Some of the applications we get, Scott, Ellsworth, you tell me, some of them are more than that just for one bridge. We know many of you have some statement bridges that you'll never be able to replace on your own, and you need help with grants and federal funds. So we're just trying to find ways, what are innovative ways that we can help reduce that number, and with things like GRS-IBS or bridge maintenance or bridge rehabs to keep the funds that we have to the worst bridges that need to be replaced. So it kind of leads into why we're here today. GRS-IBS is one of the Everyday Counts initiatives. That's a federal highways program that they've been doing since 2011, and they come out with a new list of innovations every other year. So this was introduced with round 3 of GRS-IBS, so it's about 2015. And that means that it's a proven innovation, that it's underutilized. FHWA would like states to do more of this innovation. So I know Idaho has done quite a few bridges with GRS-IBS now at this point. We've got a few contractors that have done it. It seems like a lot of them are mostly on the local system, and many of our local jurisdictions have done them with their own staff. They haven't had to hire a contractor to do the work. So that's one of the major benefits that we'll talk about later. But this is an innovation that we're trying to get more information about and get more jurisdictions comfortable with using this type of abutment system.
All right, with that, we're gonna transition over and Scott Wood's gonna take the lead.
Good morning, everybody. Yeah, this is hopefully what you came for. We're going to talk a little bit about the GRS-IBS bridge system. As Amanda said, we've been kind of pushing this bridge system the past few years because it is an economical way to replace a bridge. But I'm starting off with just your basic bridge components. This is not a GRS-IBS system. This is, as Nick said earlier, for those people who don't know much about bridges, this is just some general components of a bridge. So you kind of start off with your substructures, which includes your piers and your abutments. Your abutments are at the end. Your piers are typically within the waterway or within a median or so. On top of that, you have your superstructure elements, which includes your girders and your deck. So that's kind of what we'll be talking about today. The main components of the GRS replaces is the substructure system. The superstructure system for GRS-IBS is pretty similar to your conventional bridge type. And I believe we're starting off with a poll question to see if you were paying attention.
So 20 feet or longer is that magic number to be captured on that national bridge inventory. LHTAC has been working over the last year and a half to capture those 10 to 20 foot bridges on our small structures or our small bridge inventory so that we can compare apples to apples with what's on ITD's list, as well as advocating for funding to help support those locals and their bridge replacements and their bridge needs.
So I guess the question comes to mind, how do you define the 20-foot span length? This diagram here shows you several different bridge types to how to define the length of a bridge. Most of the time it's just the clear opening width is how it's defined as greater than 20 feet. One unusual one is the use of culverts or multi-culverts, and you can see down there if the extreme inside edges are greater than 20 feet, then it will be included in the National Bridge Inventory Database, and it will be included in ITD's inspection and load rating analysis and be reported to FHWA. Okay, so what is GRS-IBS? It's an acronym that stands for Geosynthetic Reinforced Soil Integrated Bridge System, which consists of a reinforced soil foundation, a geosynthetic reinforced abutment, and an integrated bridge approach. Thank goodness they just shortened it to GRS-IBS. Kind of a cutaway cross-section comparing to the previous diagram of a normal bridge. The GRS-IBS system consists of what we call a reinforced bearing layer in lieu of a normal concrete foundation, which most of you are used to. This is actually just reinforced soil that's basically stacked up and compacted. I believe we had a poll question here. Just off the top of your head, for those that may know or want to guess, what are some of the benefits of using the GRS-IBS technology?
So what are the benefits of using GRS-IBS technology? We've got reduced construction costs, reduced construction time, ease of construction, use of readily available materials and equipment, or all of the above. So just a few more seconds on this poll. 100%.
Yeah, I think that was a pretty easy one there. We're just checking to see if everybody's awake. Yeah, so like the switches. So yeah, here's some of the advantages for the GRS-IBS. It is a very simple construction technique. The construction time is relatively short. Usually takes weeks to build one instead of months, depending on the bridge size. Pretty common materials are used. There's no sort of fiberglass or any unusual epoxy resins or anything typically used in this. Little or no cast-in-place concrete is used. There is some grout used in some applications, but basically you can get away with not even having a concrete truck deliver concrete to your site. Requires a relatively small, unskilled labor. They do have to know some tools. You do have to have an equipment operator, but other than that, it's fairly simple construction techniques. Because you're not pouring concrete, you're very adaptable to field changes if you run into rock or other obstructions or want to change it on the fly in the field. It's not sensitive to weather conditions. You can do this in the wintertime or if it's wet a little. This system also decreases the chances of having a bump at the beginning of a bridge. One of the biggest, besides SCOUR, one of the biggest failure mechanisms of a bridge is just fatigue, and a lot of that's caused from your differential settlement between the bridge and the approach. So you'll create a bump at the bridge that will create an impact loading on the bridge, which will further damage the bridge. So with this system, it greatly reduces the chances of getting a bump at the beginning of the bridge. And so far, these bridges have had great performance. They've been out in the field for more than 20 years now, some of them, and they're continuing to be monitored. Some other advantages, these can be cost effective. According to FHWA, they can be about 25% less expensive than a conventional abutment bridges, and potentially up to 60%. Kind of two ways you can do it. The jurisdiction can either do it themselves, depending on their crew experience, or you can hire a contractor. Currently in Idaho, we don't have too many being built, but hopefully this will decrease in price the more we build, and that's one of the big things that LHTAC is doing, is trying to push this system so we can continue to get lower and lower prices as the experience gets out there. And also, this is great for remote locations. Just an example, we have a bridge we're replacing right now in Hawaii County, and the closest cast-in-place or the closest ready-mix place is 5 hours away. So we're going to be able to build this bridge system without even having a concrete truck delivered to the site. If you list the advantages, I got to list some of the limitations. Right now, they are recommending a max span length of about 140 feet, which is fairly long bridge. And also, because this is considered a spread footing type foundation system in lieu of a deep foundation system, foundation scour can be an issue. There are several ways to mitigate that. And then currently, the current research is kind of limited to the max fill height of the wall, abutment height of the wall at 30 feet. It is important to note, though, that these criteria were based on experience to date and not limitations of the technology itself. So as more research is done, these sort of boundaries can be and will be expanded as the research is further developed. So putting it all together, this is kind of a look of a bridge that was done in New Jersey. Probably a little more riprap than what we would see around here, but this is kind of what it looks like. You can hardly even tell it's a GRS-IBS bridge. Using colored block, it looks really, really great. And then this is just a cutaway cross section. We're going to get into some of the internal components of the bridge system here just to show you how the system is put together. There are about 8 different components of the bridge GRS system that you probably should be aware about. And we'll just go step by step through everything starting from the bottom. The first is called a reinforced soil foundation, or RSF for short. It's basically you dig a hole. It's kind of the foundation system of the bridge, the bottom of it. You dig a hole, you lay it with some geosynthetic, and you fill it with either well or open graded backfill, and we'll get into defining that in a minute. And the backfill can match the backfill from the rest of the system as well. The depth and width is based on what we call the external stability of the GRS system. You want about 18 inches deep, at least. And this is also very important for this when you go to construct it, is you want this as level as possible on the top, because this starts your first row of the facing blocks. So you want to start off with good level foundation so you can start your foundation blocks level. The next step in this is creating the actual GRS abutment. this geosynthetic reinforced soil abutment. It's basically you're just staggering layers of aggregate with a geotextile reinforcement. The spacing you want to keep under 12 inches thick, and a lot of that depends on how it was designed and what geosynthetic reinforcements you're using. And you do vary the length of these. As you can tell, it's sort of a slope backfill there. You do vary the length of that depending on your excavation. So you have different zones of length of geotextile reinforcement within your GRS-IBS abutment. Speaking of the backfill I talked about earlier, there's two typical types of backfill, what they call well-graded backfill, which is typically between 0 and 2 inches. And then there's the one on the right, the open graded backfill. I think most common for Idaho is this open graded backfill. I think the example we'll see later, Matt used the open graded. And I think it's readily available, and I believe it's also better for drainage, and it's probably easier to compact as well. The reinforcement we keep talking about, this geosynthetic reinforcement, it comes in rolls like this. It's not very stiff, excuse me. Comes in these rolls. They come either what they call uniaxial, biaxial. So sometimes you have to be aware of the direction of placement. It's stronger in one direction than the other. And especially on the reinforced soil foundation, if you're putting this in the wet, pay attention to the overlap of the geosynthetic as you place it. You'll have to overlap it depending on the direction of the flow of the water. Just kind of geeking out a little bit, here's kind of why this system works. If you take the diagram on the left, this is just, consider this just a block of soil, and you put a weight on top of it. What happens is that soil compresses and the sides tend to bulge out. And so you get this big bulge, eventually crack, and the failure. Well, you put, now looking at the picture on the right, you put layers of geosynthetic in there. Well, you create, and you put that same weight, you create smaller, shorter zones and less bulging on the sides. So you create a tension within each layers of the reinforcement, and you just basically create a stronger soil mass because those layers of reinforcement. Going on to the next element of the GRS system is what we call the facing elements. The most common is just your regular concrete masonry block units that you typically see on the outside of buildings, referred to typically as CMU. Important to note here, these are not considered a structural component. These are strictly just a facing element and just basically protects the GRS abutment a little bit from washing out as well. They're not grouted or mortared. They're just the reinforcement is placed between the layers, and basically friction holds them together. However, the top elements up near what we're going to discuss later, called the bearing pad reinforcement zone, the top elements you will need to pin with a rebar and grout those, and that's what I talked about earlier. You may need you will need to grout those top courses. They usually come out on pallets, so they can be pretty heavy. Like I said, they kind of serve a few different purposes, but mainly in addition to the facing and the way the overall bridge will look, it can form as for compaction of the GRS backfill, and it protects the granular fill. And you know, a lot of it is just dependent on how you want it to look, the durability of the CMU block, and even the availability depending on what you can get in your area. Another type of system that's pretty radically different than what we've been talking about before is the welded wire GRS abutment. It uses welded wire in lieu of the geotextile fabric, and the facing consists of rock instead of blocks. This system, it kind of looks like gabion baskets when it's done. So I think Hillfiker retaining wall is probably about the only supplier for this. But it's a good alternative, and it looks really good too. Going on to the system, we have a zone called a bearing pad reinforcement zone, and this is the area that sits under the girders themselves. It's about 3 courses deep, so you're looking about 2 to 3 feet deep. There's extra geotech style reinforcement in this area, closer spacing, not quite as long. But again, the facing elements in the zone need to be pinned and grouted. So be aware of that if you start constructing, that you do have this zone of additional reinforcement you need. On top of that is the beam seat. The interesting thing about GRS-IBS systems that the girder system used, especially if you use the concrete girders, don't need a bearing pad. They sit directly on the aggregate itself, which is interesting. This bearing zone is set back from the facing. You usually use a 4-inch thick foam board between the back of the facing and this bearing seat zone so that the concrete girders can sit on that. Now, if you use a steel girder system, you will probably need some sort of concrete bearing, including bearing pads. So just be aware of that. One thing to be careful of when you place these girders, especially when you place the concrete girders, you don't want the girders to drag on the aggregate. You want to place them directly down. If you drag the girders on the aggregate, you can pull up some of that rock and potentially damage the bottom of those girders. So if you do, when you do set the girders, be sure you just set them directly down and don't drag them across. One of the important features of the GRS-IBS system is eliminating the bump. And the way this is done mostly is through this integrated approach at the top. So after you set your girders, you construct your integrated approach, which is essentially more layers of aggregate and geotextile reinforcement. You do place the superstructure first and then construct this. It's very important that you create this overlap. I'm trying to show here at the end, I don't know if you can see it. This overlap past the cut of your excavation. You want about 3 feet past that so that you can, you want about 3 feet past your cut so you can minimize that bump. And that will help alleviate some differential sediment and get rid of the bump at that end of the bridge as well. The poll question here: what kind of superstructures work well with the GRS system? Thanks. Yeah, all of the above. Pretty much most systems will work with this, and I guess I put suspension bridge in there just to be kind of funny, but you know, it's a little cost prohibitive. But yeah, you could actually use a suspension bridge if you wanted to with the correct detailing. So, but yeah, sort of all GRS systems can accommodate many types of girders. Some of the more common ones are probably your prefabricated steel girders. Companies such as Big R can fabricate these, and True North. I believe True North is out of Montana, up north there. So if you're in North Idaho, they can come from there. Big R, I believe, comes from Colorado. But these are the prefabricated steel girders are a pretty neat system. They just come in and you just bolt them together. And they come with a corrugated metal decking. Precast voided slabs is another popular type. Those are just sort of rectangular slabs that go right next to one another. You don't have to pour a deck. You can put an asphalt concrete pavement on top of that. However, I would say if you do use precast voided slabs, to apply a waterproofing membrane on top of them to prevent any leaking of water down through the girders. That always helps. Your deck types depend on your system. They can be any deck type to match your approaches or different. You can have gravel, asphalt, concrete. And also consider the railing type. Most of our local system is not on the NHS route, so you don't have to meet the new MASH criteria, but you do want to meet some minimum test level criteria. So work with the designer. Your Big R bridges come with your standard guardrail treatments. And those, I believe, are TL2s for the most part, we call them. So I guess we have a little question break here. Okay, hopefully everybody's back. Not too big a deal. We're gonna start this next round off with a little short 4-minute YouTube video. This is the time-lapse video mostly of a GRS bridge replacement in Dodge County, Wisconsin. And hopefully your sound will work.
Sounds good.
In the spring of 2016, The County Highway S Bridge crossing the Shaw Brook in Dodge County, Wisconsin was destined for replacement. This 69-year-old bridge had suffered deterioration, which would soon make it unsafe to support its required loads. Instead of using traditional bridge building methods, where abutment piles are driven down to bedrock and concrete is poured in place, requiring more time and costlier specialized construction equipment, an innovative method was selected. This new bridge building technique, called Geosynthetic Reinforced Soil Integrated Bridge System, or GRS-IBS for short, uses multiple layers of a geotextile fabric wrap, a compacted granular fill, and a row of modular facing blocks. These layers are stacked on top of each other until the desired height of the abutment is reached. Then, precast girders are brought in to span the abutments. Here you can see the construction in time-lapse fashion. The existing bridge is removed. Now the sheet piling is installed. Sheet piling was used on this project due to the site conditions and high normal water. The east abutment is excavated. Then GRS construction begins. As you can see, layer by layer, the fabric, fill, and blocks are installed until the abutment reaches the required height. The same procedure takes place on the west abutment. Here, the excavation begins, and the GRS construction takes place. GRS-IBS utilizes ordinary construction equipment, as shown here. The sheet piling is removed. The pre-stressed box girders, or superstructure, are installed. During the construction of this bridge, a showcase was presented on August 25th. Local government and transportation representatives throughout the region attended in order to learn more about this new technique and see how it might be useful for their bridge replacement scenarios. And now our project is almost complete. The concrete overlay is set. Bridge railings are installed. The asphalt approaches are laid, and final touches to the highway and shoulders finish the project. It's expected that in the future, the use of GRS-IBS construction techniques for eligible bridges will result in the use of common tools and materials, quicker completion times, and an overall reduction in costs to create an aesthetically pleasing and solid bridge that will last many, many years.
I thought that was a real good video, short video, to kind of get you warmed up to some of the other things we're going to be talking about next. So basically, we're going to go through kind of what is the process to get your bridge replaced. And it's pretty much like any normal construction project. You have your planning phase, your design phase, and then your construction phase. During your planning phase, you want to look and make sure you can use GRS-IBS. Do some preliminary geotechnical investigation, and you might need to start obtaining some permits as well, depending on how long that's going to take. Then you go into your normal design phase, geotechnical, hydraulic, roadway, bridge, and then develop your plans, specifications, and if you need to, your estimate. Construction is like anything else. One thing you want to be critical of is ordering your material as well in advance so you're not stopping work. For the planning phase, this can be pretty straightforward. LHTAC has developed a checklist that we use to pre-screen whether or not the GRS is applicable for the site. It's a pretty straightforward checklist, yes, no questions, can help you determine if it's applicable or not. You will need some sort of geotechnical investigation help with that. It is a highly soil structure interaction structure. But basically, if you have shallow foundations, will work, or if it's going to be bearing on rock, it will probably work. And then, like I said before, you may want to start obtaining permits from the different agencies, which we'll get through soon. This is a list that someone here at LTAC put together for me. It just goes through some potential permits that you may need to go through, which includes Idaho Department of Water Resources. What it covers would be stream alteration permits for perennial flow, year-round flow. I'm sorry. It's not needed for intermediate. Yeah, that's true. The big one here is probably the U.S. Army Corps of Engineers Joint Application 404 permit, which includes wetlands and water work below the ordinary high water mark. The Corps will help you with obtaining other things such as the wetlands, endangered species, cultural and tribal coordination if you need it. And then there's the Idaho Department of Lands for certain rivers, and also the Bureau of Rec for some irrigation. The rules and regulations on environmental are constantly changing, and luckily here at LTAC we have Carissa and Joellen to help us keep track of that. So if you ever need any help with that, please reach out to Carissa or Joellen here. Next, you'll probably want to hire a good experienced design consultant that's done GRS-IBS systems before to help you come up with the detailing of this. There is a lot of detailing required, a lot of design to come up with on the GRS-IBS system. You don't want to come up and have some sort of conflict arise in the middle of construction. So make sure you hire experienced design consultants. Typically, the scope of work is smaller for these type bridges, especially if they're non-federal aid projects. This is a flow chart that was in an FHWA manual, which I'll talk about later, that kind of establishes the design flow of your project. You'll want to define the project parameters, do site evaluations, determine if you can use it. Some of the things, calculating loads, external stability, and internal stability, that's something that is highly specialized and should probably be done by somebody who knows what they're doing there. And then finally, you want to develop the plans that can be built and create construction specifications, especially if you're going to hire a contractor to do this. Some geotechnical considerations. We talked earlier about bearing resistance. This is how much weight can be bared on the existing soil. Also the reinforcing strength. Somebody's going to have to determine what type of geotextile fabric to use and your spacing of those. Your external stability, which includes sliding, bearing resistance of the soil foundation, and global stability. You don't want this thing basically to create a small miniature landslide due to your granular fill and the weight of the superstructure sitting on top of this. You want a geotechnical engineer to select your backfill, whether it's well graded, open graded, or help you determine the source for this backfill. In some cases, you may need to consider seismic design. Not too much here in Idaho, but sometimes you do need to consider that as well. Hydraulic design is another important consideration. You'll need a hydraulic person to determine maximum flow, to determine how high your bridge needs to be, how high over the water it needs to be, which we refer to as freeboard clearance. Typically, you don't want the water to hit the girders. You don't want the water to overtop the roadway. Very important with the GRS foundation, since it is considered a spread footing foundation, you do want to consider the SCOUR implications and know how to mediate for SCOUR, prevent SCOUR from undermining your abutments. Also very important, if you're dealing with FEMA floodplains, you need to get some permits there, work with your floodplain developer, local floodplain development, and get a permit for that too, probably. As I said, SCOUR, most of these in Idaho will be built over waterways, not typically over a roadway. So SCOUR is an important aspect of this. One way to do it is basically put your reinforced soil foundation below your SCOUR depth, which was your SCOUR depth is determined by your hydraulic design and your geotechnical analysis combined. Some other ways to remediate it is to place the riprap, properly sized riprap at that. And that's part of the hydraulic analysis based on the flow rates through there.
Scott,
Cool.
you had a question in the chat box from Art that said, how would GRS abutments work or perform when they're submerged in the facing? And I thought it might be good to talk about it on this slide.
Well, typically you'll want to dewater it just from a safety standpoint. So usually you need to create some sort of cofferdam or water diversion when you build these. You don't really want to build them within in the water itself. I think the video we showed sheet pile cofferdams. That's probably the more extreme version. Some of them could be as simple as just piping the creek or sandbagging, or I've seen traffic barriers lined with visqueen to create sort of a channel to direct the flow away from your construction. So.
But long-term stability and everything else, they have been known to be working within the water once they're constructed.
Yes, absolutely. Yeah, they will work within water, and like I said, in Idaho, most of these will be built in water, so you do need to account for that. One way to determine scour is this picture on the right here, kind of innovative, is to use different color facing blocks. So you can see the sort of red facing blocks there will actually be buried. So as the soil scours away, if it does, the red bricks will start to be exposed. So it's a neat little advantage of using the system and measuring the scour if you have any. Kind of moving into the construction aspect of this, kind of a step-by-step. The first thing you'll usually need to do is remove the existing bridge. One thing you need to have, typically you're working with a lot of heavy concrete components, so you'll want a removal plan. You don't want a lot of things falling into the river or the creek. Make sure you use the proper equipment. Like I said, some of these components can be heavy, so you want to have equipment that can lift these large components. Be aware that sometimes these old railings and stuff will have lead-based paint in them. And also sometimes the concrete will have asbestos in them. The tests for those are pretty cheap if you're concerned about it. I think you can get them done $1,000. Also, you'll want to probably typically remove the existing foundations, especially if they're going to be in the way. You want to remove those below grade. However, if they are a deep foundation, typically you can just cut them off 1-2 feet below the surface and be okay. You don't have to remove the old timber piling all the way out. Be aware of disposal. Have that disposable facilities planned out of where you're going to dispose of your old bridge. Get in a little bit of excavation dewatering. Usually the slopes will satisfy OSHA temporary slopes, but be aware if you have any other temporary slopes, make sure they follow your OSHA criteria. You don't want to endanger any lives there. We talked a little bit about dewatering, which can include just simple pumps if you need it. If depending on how your excavation goes, maybe you don't need, you can use the existing soil to sort of create a dike system there, but you may still need some pumps. I mentioned culvert diversion, which Matt will talk about later. That's what they used on theirs. And probably the most extreme is a sheet pile cofferdam. That's probably for high water streams. And also that excavation will typically follow the slope of that GRS abutment. Compaction is fairly simple in the GRS system. Most of the time you just use a vibratory plate compactor. If it gets a larger system, you can use a smooth drum roller. Just be careful not to get too close to the facing blocks. And sometimes if you work with your geotechnical engineer, you can maybe not even need any testing for the density. Maybe just you would have to count the passes of your roller or your vibratory plate compactor, and that might be sufficient. You might need to do some testing at the beginning to make sure you are getting proper compaction based on the number of passes, but sometimes you don't even need to test. One thing to be careful of is block movement. I think we've had a couple of projects here where the blocks tend to get pushed out. One recommendation from FHWA is to have people stand on the blocks because they are just based on friction. So you don't want to put too much heavy compaction equipment close to it. But if you can put additional weight on those blocks, it can help prevent the blocks from moving out as you compact it. One creative method too is also actually using the existing abutments. This is one Matt's going to talk about later, Ruby Creek. The abutments were in fairly good condition, maybe had some scour issues. But you know, you can fix the scour and maybe even pin back the abutments if you need to. And you can actually just use the existing abutments as your facing element. And you can also use them as a temporary or permanent solution too. So if you can actually use them for dewatering as well, if you can keep them in place for dewatering. Be aware of stormwater and erosion. You know, make sure you're using your silt fence and your fiber wattle to prevent contaminants from entering the stream or any other areas you don't want to. Some of the typical equipment that's used to construct these GRS-IBS abutments, I mentioned earlier, a vibratory compactors, track-hoe excavator, you saw it in some of the pictures. Some of the CMU blocks come in pallets, so I don't know if you want to move those around, you may need a pallet fork for the excavator or loader. Some pumps for dewatering, and probably a backhoe to move some of the backfill material or structural fill material around. Some typical measuring devices, we do need to build some of this sort of level. We're not building watches here for sure, but we do need probably some basic surveying equipment, some straight lines, some level tape measures, make sure everybody has a tape measure, you know, plumb bobs. You do need to have some minimum tolerances there. And as far as work crews go, you want to kind of optimize this. You do need one equipment operator who kind of directs the flow of things. But other than that, the rest of the crew is just kind of laying down the fabric, putting them in the blocks and spreading up and compacting the backfill. So typically crews are 3 to 6 members and one equipment operator. You do want to consider placement of the excavator and not have to move that around a while. You can see in the picture, it's kind of placed at the top of the slope there. And usually they can reach most of, depending on the size of the excavation and excavator, they don't have to move around a whole lot. Sometimes you can't have too many crew members. You definitely don't want that. You don't want a bunch of people standing around or a bunch of managers watching what you're doing. So be aware of that. You know, one big thing that always comes up is cost. We are trying to save money here. We are trying to do this cheaply, but quality-wise too. We want these things to last. Finding cost on this, because it is such a new innovation, is very difficult. They're highly, highly variable cost. But like I said before, the more we do these, hopefully the less they will cost. And they're variable basically on a few things, including type of crossing, the span length. Typically, the shorter the span length, the higher cost per square foot. And also the abutment height has a lot to do with it because that's just more materials, more labor, time out in the field. And even with your own crew, you will get greater savings with more crew experience. So if you are able to use a local crew, the more experience they get, the less time they should be out there, and time is money. So hopefully it'll come down. You know, is it with any construction project, the big 3 ticket items are materials, equipment, and labor. Materials vary in cost. Equipment, depending on what you have in stock, you may have to rent the equipment. I believe up in Boundary County, they rented some equipment very easily that helped them out doing it. It wasn't too expensive. And then labor, you can either hire contractors or potentially use your own crew forces for the labor. I just threw some numbers in here just to try to put some numbers in here. So a typical bridge for federal aid construction, non-GRS, is typically $325 to $420 a square foot deck area. That's how we usually define it preliminarily. According to some sources, you get about 25% less depending on where you live and how much experience you have for GRS-IBS. So then you're looking at around $245 to $315 per square foot, just cutting that down from the other cost. And I just kind of ran some quick numbers for a 40-foot long, 26-foot wide bridge, which is about 1,040 square feet. You're looking anywhere from $255 to $330 in construction. It's probably a pretty low right now. And And be aware that is just construction costs. That doesn't include design or if you need construction inspection costs or anything like that. And so really what I'm trying to get at, these costs are highly variable, and that's probably something you need to look at in your planning stage. Have help with that because it is a highly variable cost. But hopefully in the long run, these will be cheaper. That's LTAC's hope and goal, is to get these things as cheap as possible. So a little question break here. If anybody has any questions, we'll take them now or take them at any time, really. Nothing in the chat box, Don?
Nothing in the chat box. Pretty quiet group.
Okay, well, I've got another little video, and I won't say little, it's 20 minutes long. It is a video produced by FHWA. It's another construction, kind of goes through the process as well. You may see a lot of repetition, but that's the way you kind of learn, is through repetition. So hopefully you get a lot out of this video as well.
Conventionally, reinforced concrete piers have been the support structure of choice for modern-day bridge construction. However, as technology advances, convention seems to be shifting. There's a new kit on the block called Geosynthetic Reinforced Soil, or GRS, and it's changing the footprint of many modern-day structures. Although geosynthetic reinforced soil has been around a while, its use as part of an integrated bridge system, or IBS, is fairly new.
The concept of reinforced soil, geosynthetic reinforced soil, came about in the early 1970s when the U.S. Forest Service used non-woven geotextiles to build burrito walls, wrap-faced walls in steep mountain terrain for logging roads. Colorado DOT, during that time, took notice of what the U.S. Forest Service was doing and refined the technology. In the early 1990s, about mid-1990s, we used the technology. We've actually built a full-scale experiment here at Turner Fairbank Highway Research Center in McLean, Virginia, to demonstrate the load-bearing capacity of reinforced soil. We determined that it's extremely predictable when you build it in a closely spaced fashion as we do today in the IBS. And a couple of years later, we were given the opportunity here at Turner Fairbank to build the prototype IBS. After the success of that project, in the early 2000s, the FHWA introduced the Bridge of the Future initiative. And we piggybacked on that concept, and we continued to work with the DOTs and with the locals to seek out projects to build GRS abutments in the IBS.
In 2005, Defiance County, Ohio built the first production IBS system, the Bowman Road Bridge. Today, that bridge is performing very well, and as a result, the county has built 23 other bridges using the GRS-IBS system. In 2010, St. Lawrence County in New York took notice of the successes in Defiance County, and are now using the technology to replace many of their own bridges. How does the GRS-IBS system work? The GRS-IBS is supported by a Reinforced Soil Foundation, or RSF. The RSF is an economical, shallow foundation consisting of layers of geotextile and compacted fill. The GRS abutment, an integrated approach, is engineered to accommodate settlement, allowing for a smooth transition from the bridge onto the roadway, thus alleviating the bump at the bridge, normally caused by uneven settlement. Constructing a GRS abutment is often described as being as easy as 1, 2, 3. It requires placing a row of facing block, a layer of granular fill, and a sheet of geosynthetic reinforcement, and repeating the process up to the specified height of the abutment. This method has been proven in the field to facilitate quick and efficient construction with impressive results.
It's fairly simple once you understand the concept that by putting the sheets of geotextile in the compacted stone, that it behaves as a composite and has engineering properties. It has a stress strain curve that's fairly predictable. You're really designing these abutments as a gravity wall.
To fully benefit from the rapid construction available using GRS technology, it is important to follow guidelines for GRS abutment construction. First, since all other courses of block are built off the first row, make sure that the bottom row is level and even. Second, for optimal productivity, use only the crew and equipment necessary. Divide the labor into 3 basic steps. Step 1, laying the block. Step 2, placing and compacting the backfill. And Step 3, laying a sheet of geosynthetic reinforcement. Finally, limit the movement of the excavator towards the back of the abutment, where it can reach and place material without having to be moved.
The whole process is fairly rhythmic, fairly routine in terms of once you get the concept down of stack and compact, it is a very repetitious process that once that idea is learned, the rest of it just becomes kind of a rhythm that the wall just constructs.
Because of the simple process, a large crew is not necessary to successfully construct a GRS abutment. A typical construction crew consists of laborers and the equipment operator.
In comparison to a traditional bridge, the GRS-IBS system, I'm going to tell you, is 10 times more simple for your average layman to build. Like I said, you can take most road construction people, they don't even need to be bridge people. You can start at the bottom. Within a few weeks, you can have a bridge standing.
Specialized equipment is not required to construct a GRS abutment. Readily available tools like hand tools and measuring devices are all that's necessary. Heavy equipment, such as a track hoe excavator and a walk-behind vibratory plate tapper, will also be needed. The first step in constructing the GRS-IBS is site preparation. Since GRS technology requires building from the bottom up, staging and delivery of the material should not hamper continuous construction. It is important that diversion trenches be placed around the perimeter of the site to divert any water. As with construction of the GRS abutments, site preparation is also fairly straightforward.
It's a fairly simple process of digging down to a known elevation for the foundation to begin. And once you've reached that elevation, you can start building or constructing the wall from the bottom up until you reach the desired elevation at the top.
Once the site layout and excavation are complete, it's time to begin constructing the reinforced soil foundation. The base should be cut smooth, sloped to drain, and excavated to a uniform depth. All loose, unstable material should be removed, backfilled, and compacted to provide a good foundation. Laying the reinforced soil base can typically be completed in 1 day. The next step in building the GRS-IBS is to encapsulate the soil foundation with geotextile to prevent erosion. Typical spacing in the reinforced soil foundation is 12 inches. Once the soil foundation has been fully encapsulated, compaction begins. Place the fill from the back to the edge of the RSF and roll out any folds or wrinkles to the free end of the layer. The soil foundation should be backfilled in compacted lifts not to exceed 6 inches. The final step in this phase is building the GRS base. The typical base is constructed with split-faced concrete masonry units and compacted backfill. Properly compacted backfill is crucial to GRS-IBS performance. Compact all areas behind the split-faced concrete masonry units so that no voids exist below the geosynthetic reinforcement. A thin leveling layer of fine aggregate can help set the CMU blocks to grade and prevent them from rocking. The leveling layer should be kept to a minimum thickness of no more than 0.5 inches. Before placing the geosynthetic reinforcement, it is important to sweep off any granular fill from the top of the block. This will prevent cracking of the facing blocks. The GRS project will determine the number of reinforcement zones needed. Reinforcement zones represent different lengths of reinforcement away from the wall. Roll out the geotextile so that the greatest reinforcement strength is perpendicular to the wall face. Where one roll ends, the next roll should begin. Overlapping between the sheets of reinforcement is not required. Any excess reinforcement material should be removed with a razor knife or a propane torch. Preventing wrinkles in the reinforcement material is crucial. Therefore, place the fill from the wall face backward so that any wrinkles that do form can be removed. Construction of the GRS abutment continues with alternating layers of compacted granular fill and geosynthetic reinforcement according to the design plans. As the abutment wall is being constructed, it is crucial to maintain the proper wall face alignment. Check the vertical GRS wall for plumbness at every other layer. Any deviation greater than 0.25 inches must be corrected. As the upper layers of the GRS abutment are constructed, a bearing reinforcement bed is constructed to provide additional strength to support the increased loads due to the bridge. The bearing bed reinforcement serves as an embedded footing within the GRS abutment. The spacing of the reinforcement in this location is half the primary spacing, or 2 layers per course of block. The depth of the bearing reinforcement zone is determined based on the internal stability design for required reinforcement strength. At a minimum, there should be 5 bearing bed reinforcement layers. For a bridge with super elevation, it is important to ensure that the minimum number of bearing bed reinforcement layers beneath the beam seat is installed across the length of the abutment face. At this point, the reinforcement layers become stair-stepped, with reinforcement terminating along the angled surface of the elevation. Pinning and grouting the upper 3 courses of block completes construction of the facing wall. It is important to suspend any construction activity near the face once the top of the wall has been pinned and grouted to avoid wall displacement. Once the abutment wall is completed, the beam seat is constructed directly above the bearing bed reinforcement zone. The superstructure will be positioned on top of the beam seat. Proper beam seat construction begins by placing 4 inches of pre-cut foam board on top of the bearing bed reinforcement. It is important to make sure the foam board is butted against the back face of the block. Next, place a solid concrete block on top of the foam board across the entire length of the bearing area. The final step is wrapping the layers of the compacted fill. The thickness of the wrapped layers is essential to maintaining the final beam elevation. The fill thickness of the first 4-inch wrapped layer should be compacted to the top of the foam board. The fill thickness of the second wrapped layer should be compacted to the top of the solid block. The top of the second layer controls the beam elevation. Therefore, it should be carefully compacted and graded. As an option, aluminum flashing can be installed after construction of the beam seat and prior to setting the bridge beams. If used, the flashing serves as both a drip edge and a clear space filler. Place the flashing between the bottom of the beams and the foam board. Make sure the length of the flashing extends beyond the outside of the bridge beams. Finally, trim the flashing so that it fits against the parapets. Placement of the superstructure occurs following construction of the beam seat and flashing installation. Make sure to set the beams so that they are square and level. Never drag the beams over the beam seat surface. The wing walls and parapet are constructed following placement of the superstructure. First, trim the split-faced concrete masonry unit in the parapet wall for a custom fit against the beam edge. Next, fill the space between the superstructure and the facing block with thin layers of cut block or mortar mix. Following completion of this phase, approach construction can begin. The GRS integrated approach is constructed of aggregate layers, reinforced and wrapped with geotextile that blends the approachway to the bridge deck to create a smooth transition. It is important to use well-graded material throughout this phase and to trim the geotextile reinforcement to the prescribed length after it is wrapped. Repeat this process until reaching a height approximately 2 inches from the top of the beam grade. The wrapped layers are then placed behind the beam end. There are a few guidelines to follow for pavement of a GRS project. First, during paving, it is important to keep the top layer of reinforcement approximately 2 inches below the beam grade. This will allow a layer of aggregate cover to be placed to protect the geotextile reinforcement from contact with hot mix asphalt. Also, the paving fabric should extend 3 feet over the bridge deck onto the approach. Finally, if guardrail installation is part of the project design, it is recommended to use steel H-posts for any railing that is driven through the reinforcement. It is also possible to drill through GRS with an auger to set other types of posts. These procedures for constructing a GRS-IBS have been proven in the field to facilitate quick and efficient construction. Additionally, GRS-IBS provides faster project completion at a reduced cost because the design is flexible and therefore easily modified in the field.
The biggest benefit to the GRS-IBS system is the adaptability to the different sites. Again, the over-excavation that's not required as part of this. We can put it on unsuitable soils. We can put it in water environments where we would normally have to have piles for standard concrete. It's obviously it's cheaper, it's faster, and in these economic times that we're in now, it's cheaper and faster is obviously a big factor.
It's not traditional, so to look at it from the outside, it looks to be a little bit, you might question it, but once the construction process starts, you can quickly see how easy the concept is and how flexible you can be in times of construction with, rain, weather. It doesn't really shut anything down in terms of moving the construction process along.
There are 3 primary advantages for using the GRS-IBS. It's faster, more economical, and easier to build than traditional bridge structures. Additionally, research indicates that its long-term durability will be better because it has fewer parts and because the substructure and superstructure are blended with the approachway to create a jointless bridge system. The GRS-IBS system doesn't have many of the common elements associated with a traditional bridge, particularly those leading from the roadway to the bridge. For example, it doesn't have an approach slab or a sleeper slab, and it eliminates the bridge bearings. GRS-IBS is not for every bridge building assignment. It is, however, a perfect solution for smaller, single-span bridges. The system is currently tailored for single-span bridges up to 140 feet. The longest bridge constructed to date is a 140-foot steel girder bridge. That bridge is performing very well, even throughout its thermal cycles. There have been no adverse effects seen on the approachway. GRS-IBS is great for grade separations, although the bridges completed to date are built over streams with non-scour conditions. It is a shallow foundation system and thus not suitable for scour critical areas. However, the technology works very well for both steel and concrete superstructures. In Defiance County, the first bridges built using the GRS-IBS provided them with a 21% cost savings. Today, Defiance County is saving up to 40% on their bridges because of their ability to rapidly construct the substructure. They understand how the technology works, and the labor crew is well trained. In St. Lawrence County, their savings are even greater because in their previous design methodology, they include many of the details associated with a traditional bridge, such as the approach slab, the sleeper slab, the bridge bearings, and the parapets. With the GRS-IBS, you don't need those traditional elements. St. Lawrence County has realized a savings of between 50 to 60% on all the bridges they are currently building. Recently, the interim implementation guide for GRS-IBS was completed. This guide is the result of about 40 years of research. It consists of 2 volumes, one specifically for the design and construction of the GRS-IBS. The other volume contains a census report of all the available research supporting the design and construction of the GRS-IBS.
For others thinking about GRS, the thing to do first is kind of get comfortable with it in terms of how it works, understand the fact that there's a lot of data that shows that you can trust that if you put it together this way, you'll get the kind of performance that we've seen. And then to get comfortable with the actual construction. It's been a good fit for us.
I can quite sincerely say that from the beginning of researching this technology, it has amazed me with each experiment. It's so far exceeded our expectations. And when we built the IBS, designed the IBS, we redesigned the bridge where we got rid of all the common elements associated with the bridge and redesigned it from the bottom up. I think it could be used in the interstate system once people take more notice of its long-term performance on these local road systems. I truly believe the technology has a home in all facets of earthwork, not just in bridge support applications.
The many advantages GRS-IBS technology offers make it a viable choice for many bridge projects.
So if you're still awake with me, interesting stuff there. So the FHWA report is available online. It is a little over 100 pages. It's a very good reference for the design and construction of it. If you need help with the link, I can provide you that. Any questions after that video? Any chats or anything come up? Okay. I think next I'm going to kick over to Matt Hall with HMH. He's up in Coeur d'Alene in North Idaho. He recently worked with Boundary County to replace a bridge up on Ruby, I think it's Ruby Creek Road, Ruby Ridge, the infamous Ruby Ridge area. So I'm going to do my presentation here. And Matt, you can take over.
All right, I think I've got screen shared. Everybody see screen?
Looks good.
Thumbs up, thumbs up. All right, so yeah, as some of you might be aware, this is kind of our second go at the presentation here. We did have a on-site presentation at the Highway District, or at the Boundary County shop, covering a lot of the same information Amanda and Scott have already covered. So I'm gonna kind of skip through all that, kind of just hit on the highlights of Boundary County, the bridges there, and then kind of the highlights of the construction part. We actually went out to the field, got to see crew kind of doing the work. So for those of you that didn't make the last trip, you'll kind of get a feel like you were in the field this time. So yep, Ruby Creek Bridge number 3. Let's see, why are we here? So Boundary County, 37 local bridges, several in really poor condition, similar to a lot of highway districts and counties, cities, municipalities in Idaho. It's an issue that everyone's dealing with. They have 4 of them that are posted. I say 4, but actually, hopefully here soon. The load rating is getting done on Ruby number 3, so hopefully that number will drop down to 3. Key here is, these bridges, these 25 under the 65 foot, right? These are the bridges we're talking about. These are the bridges that Boundary County is trying to take care of themselves. They've got some other bridges. This process doesn't work for it. It's not gonna fit into that. It's gonna be the federal aid process. They're gonna need help replacing those when the time comes up. So that's kind of an idea. I drop this over here. Can you guys all see that? Kind of give you an idea of where this bridge is. If you're not familiar with Boundary County, Bonners Ferry. Yes, this is the infamous Ruby Ridge. Naples is just down the road here, so that's where we're background on Boundary County, from posting the legal loads, you know, how do we get there, repair or replace. You know, the Chinese New Year doesn't necessarily follow January to February, kind of like the bridge year. I don't know what we want to call it, bridge inspection year, right? It begins when you receive the inspection reports, right? So 2019 to 2020, Boundary County's inspections are usually done late summer. It's when the streams are down. So here it comes in September, right? 2019, 2020, we want to kind of call it the year of the rubies. So there's 4 bridges on Ruby Creek. Started out early March 2019. Ruby Creek number 2 was posted. This is an interesting bridge because it's exactly like Ruby number 3. So all these bridges were built in 1975. There was a big flood through the area, wiped out the bridges that were there. These came in, someone came in, built bridges out of whatever parts they could find. Ruby number 2 is slated for a federal aid bridge replacement. It's actually done. It was supposed to be built this summer. It slid because of some funding. So replacing it really wasn't the best option for the county. So with some, you know, creative engineering and reuse of existing materials, they fabricated a temporary bridge deck out of some old bridge beams that they had, salvaged from another bridge replacement that they did. Actually got that load rated and put it in place, and Ruby number 2 is back open, non-rated, ready for use, still in use today until it'll be eventually replaced. Ruby number 1, here we are in June 2019. This is another one of these. This one kind of used some, I guess what I would call kind of early ABC bridge technology. They had no as-built for any of these bridges, but what it appears they did is precast all the elements, cast in place a footing, and then with these weld ties, hooked everything together in the field. Well, the weld ties from our investigation are kind of in bed with about, looks like number 3 rebar, rusted out. They have all started to fail. With that failure, the back wall abutment started to slide forward. It was actually about 5 inches protruding out, 12 inches of bearing. So it was getting close to failure. So designed a tieback system and a little corbel at the bottom, put that all in place. It's all been passed now. Everything looks great. That's all done. There's Ruby number 1. And then Ruby number 4, I don't have any photos of it, but another one of these cast in place concrete abutments, and they had steel girders on it. It just needed a new deck. So the county went in there and put in new deck pans and serviced number 4. And then number 3, the bridge we're talking about here, so built in 75, 22-foot, single lane road, no alternate access. So this Ruby Creek Road, it's the only way up and in and out of there. You know, there's a dozen residents up there. There was for a while a school, a private school, just between Ruby number 2 and number 3. It's now been closed for a while, but it's still there. Could come back. You know, good access for timber sales. They're going to hold a timber sale late this fall, early next spring. Up in here, fire access, emergency vehicles, all that. This is kind of the way in and out. You see the existing deck. So the inspection report, we pull up number 3. You see report on it. The deck was a 5, the super was a 5, and the substructure was a 4. So it did create a little bit of confusion when we actually received the load posting, because the superstructure rating was better than the substructure. So initially it looked like there was some SCOUR issues, which there are with abutment number 2, and as Scott mentioned, easily correctable. So after conversations with ITD, the fact that this built up deck, there's thoughts that maybe it's a railroad car frames with concrete poured on top of it. I know Scott Woods thought maybe it's old railroad girders, the web from railroad girders. No one really knows what it is, but it's not in great shape. So here we are, we get the dreaded bridge posting letter, and like I said, single lane road, we're coming into winter, right? This is October 31st. Bridge needs to be posted at 6.4 tons. Well, due to the narrow, windy road, the only propane truck that can get up there is not legal. So with a lot of help from LHTAC and ITD, working with the propane provider about how full their truck should be when they make these deliveries, we were able to get that taken care of. Fire department, they still had concerns, but at some point, it's the only way in and out, so we're going to take care of it. The county, Boundary County was very fortunate because, the thought of replacing Ruby number 3, right? It's beyond repair. It's a replacement. The thought of replacing it wasn't daunting to them because they previously replaced 2 bridges. In 2018, they did Caribou Creek Bridge, and they did, and these are the modular steel bridge systems. They replaced a 20-foot opening with a 65-foot bridge here at Caribou Creek. They also did Snow Creek Bridge, and these are in the general same area of each other. This is a 20-foot bridge, replaced it with another 65-foot bridge. Interesting note, Scott kind of ended on the cost of this. The county replaced both of these bridges for out of pocket less than $200,000. They did receive some grant money to help with the procurement of the bridge, but out of pocket, both bridges with less than $200,000 replaced. So the thought of replacing Ruby number 3, not a big deal. Let's go do it. These guys have done it. They're capable of doing it. So, kind of the replacement process starts, and I'm not going to dwell on phase 1, all the information Scott covered, but how do you get started? Right, survey, geotech, and permits. Can't stress the permits enough, but you see here we are, early February, and the sun doesn't shine in this canyon for 3 months probably over the winter. So, some struggles with survey, just getting there in general, but work on that. The geotech portion, we're on bedrock here. There's existing abutments, things look great. They actually SCOUR, when you look at it, these abutments were cast into bedrock. So the places where it's scoured out, it's just defines out and looks good. But the GRS idea kind of started playing in, and Scott Wood's probably going to cringe, but I did email him the sketch after our first visit out on site, talking about what to do, and we're just kind of brainstorming here, like what options are there, and you kind of get into the design information for GRS, and they talk about all these different facings, and the one question earlier about gadians, yeah, there it is. So the facing, the key there is it's not structural, so that's great. we've got this abutment, it's there, it's been there for 45 years. You know, we don't know the structural integrity of it, you know, the strength of it, you know, the thought of just setting a new deck on top of it, you know, can't be comfortable with that. There's no as-built, we don't know anything about it, but the thought of using it as spacing for this GRS system seemed like a great idea. It seemed like it would work just fine. So, you know, here we are, we're kind of more in this situation right here where we're reutilizing, you know, the existing walls. So, you know, when you think about your facing, I mean, they talk about auto tires and precast panels. And, it's just there. Here's an example with no facing, which would be fine for a short-term period, but the UV stability of the geotextile is not great, so need to protect it. So there's our geotech covered. Next is permits. Kind of cheated a little bit because we knew that Ruby number 3 was coming because Ruby number 2 had already happened. So the thought of doing something there kicked off the permit thing early on, and the county's really good about applying for permits and taking care of that. So they actually started on permits before the posting came. They kind of knew it was coming. It's important to get that process started early, and also to follow back up on your permits a little bit before construction. Make sure, you know, things haven't expired or you need to update anything. So now we kick into the actual replacement, what I kind of call phase 2, the design and procurement and then construction. Design and procurement on this project kind of went hand in hand. The need to get a superstructure procured early kind of helped drive that. Now here we are with COVID and the delays with the manufacturers. Precast elements are taking a year to get box culverts. The modular bridges are starting to stretch out. I know, you know, it doesn't look like it's going to get better anytime soon. So under $50,000 projected, able to just kind of work through the process. You know, if you get over 50 and you're going to need to follow the procurement process, you know, then you're going to kind of stretch out your project a little bit. Here you kind of see here's the bridge components delivered into the county's yard. So, you know, here we are, single lane bridge, up a canyon, single lane access. Let's make sure we get everything delivered, then go put it together. So there's our parts. And here we go, starting into the construction. And I've got a poll question I think Dawn was gonna pop up for everybody.
Yeah, so we've got another poll question, just kind of checking in with everybody. How long do you think this project took from start of engineering and permitting to final completion? So our categories we have is less than 6 months, 12 months, 18 months. Let's see what you guys think. So we're just checking in with another poll question. We'll give you guys just a few more seconds. Encourage you guys to click on our poll and see what you think. How long do you think this project, Ruby Creek Bridge number 3, took from the start of the engineering and permitting to final construction? So I'm gonna close this one up. So we've got some mixed numbers here. So about 53% said it took less than 6 months. 40% said about 12 months, and 7% said 18 months.
Yeah, so, you know, like I said, with the permitting, I might have kind of tipped the hat a little bit. My answer to this is less than 6 months. The initial permitting wasn't driven directly with the bridge replacement. So if we said truly we started in the beginning of February and at the end of July, this thing was done. So even if you go back a couple months, it's still less than a year. So the timeline for this process versus the federal aid bridge program is night and day. So it's a great process. Local project, local funds. The other poll question that I didn't have Dawn put up, but something everybody just kind of think about, maybe get an idea in your mind. How many construction days did it take the county forces to replace this bridge? So think about that as we kind of work through, and you'll see at the end here. So day one, right? Staging, setup, and traffic detour. Day one was a big day, mostly because what do you do when you're between a rock and a hard place? So the hard place, I think anybody who's in construction knows right now, is the utilities. It's tough to get them out, tough to get them to relocate, tough to get them to respond. So we were fortunate we had some good help there, and we needed to build a detour route through here. So we need to move the utility, we need to move some rock, and what you do is you just move both. So, you know, iron and steel went over rock every day. The county was able to make a little more width here. We got the utility hand dug back. We pulled the pole, tied the line back up in the tree, and here's our detour route. So, you know, big day, day one. Got the detour put in.
Yeah, that's something to note, Matt. You didn't just close this bridge. You had it open the whole time.
Yeah, the other two bridges, Snow Creek and Caribou, I previously showed, the county was able to close those roads and just detour people around. So this one was another challenge. It was a challenge permitting wise, right? We got a stream crossing permitted, pole joint permit, Corps engineers, water resources, pole trout area, all those requirements in place, and you know, it just adds to it. So that 6 month, 8 month, even a year with that process, I still think it's pretty awesome that it can all kind of happen that fast. Here we are at day two, preparation of the GRS Abutment 1. So, you know, county has a lot of new folks. This is a big project for them. You know, they're doing a lot of the typical county maintenance activities and work, but you know, these guys are going to go replace a bridge. So excitement, apprehension, all those things. I like this photo because the excavation here, if you can make that out, these are all grader bits. So, you know, typical Idahoans, right? We don't waste anything. We need a little back wall filler from the homemade bridge, and we need some old grader bits. One thing to note here was these existing abutments. Scott and I discussed a little bit. You know, we have no information on them. We don't know how big footings are. We don't know what the integrity is of them. You know, they look solid, but the decision we made was we're going to add some tiebacks. So here's the crew kind of core drilling. We wanted to tie them back. It is interesting to note that through the core drilling process, we found out that they do have rebar in them, quite a bit of rebar, and cost a few core drill bits. So sometimes you learn the hard way, and we learned. But belt and suspenders, the existing abutments aren't going to tip over, and they have tiebacks. So day two continues. Here we are, right? So it's just kind of the process, right? Here's the process. You know, after about 2 lifts, everybody finds their place, right? You know, fabric, gravel, compact, fabric, gravel, compact. You know, the rhythm. It's a rhythm, and it's important to know that, you know, don't have too many people. I mean, it's a small site, it's a small area. Too many people, too much equipment is just going to slow you down. So, you know, the right amount of people, right amount of equipment, and it becomes a very efficient, quick process. Here's kind of a, you know, a little break in the repetitive was, okay, we're going to install the dead men in the side axe. So there's that process. And there's the end of day 2. And you'll notice through a lot of these pictures, the smiles on the crew's face. You know, these guys are excited about what they're doing out there, and you can see it, you know, being out there with them, and the fact that they can do this themselves is big for them. So into day 2, a little different process than Scott talked about, right? Why wouldn't we remove the existing bridge deck first? Well, our detour route was functional, but it was narrow. I mean, we are North Idaho, we are up past Naples. People know how to drive a backwoods road, but at night, the thought of keeping them on the existing bridge was just a little extra safety. So everything we did through the first few days was geared towards put it in, put the old bridge back in service, and go away for the night. And so here we are with day 3. And, you know, not much to say. I mean, it's repeat of day 2. The note here was some of the hottest days in North Idaho that we had had so far. By day 2, day 3, that repetitive rhythm was kind of the drag. So like, oh, we're gonna do this again, but very quick. These guys got this side done quicker, faster. This is the day we came for the field visit. I actually had to call them at one of the breaks and tell them to slow down so that we could all see something when we got there. It was like, go sit in the shade, wait a bit. Everybody's coming and they need to see something. So, other than this. So, the process is the process. Once it's down, it's pretty quick, pretty efficient. It kind of rolls right through. So, more of the same, more, you know, wash, rinse, repeat. Here we are. Day 4. So, for this superstructure, they elected to use the modular steel bridge components, bridge system. A lot of that's just, it's something they're familiar with. They're lighter elements. They can lift them and move them with their own equipment. They don't need a crane. The delivery timeline is a lot quicker. The precast yards around here, like I said, we just called for some box culverts for another client. They said a year. So box culverts are a year. I don't know how long it would take to get some voided slabs. It's drug out. So with the steel girders, they need a concrete sill to sit on. They need something so they don't rotate. Not like the voided slabs or those that are just going to sit down flush. So here we are laying out the sills, surveyors on site, and thought this was a great picture. Everybody else was waiting, and you know it's that now's the time to kind of be precise. Let's get things right, dialed in. Right, we're going to set these sills. We're then going to set the modular bridge on top of it. There's a little bit of play, a little bit of adjustment with the modular bridge system, but you know, just like if you're putting the blocks down for the facing, that first step, right? Get it as best you can, then you have some built-in tolerances in the wall. So here's the precast sills, and if you haven't seen these, it's kind of a neat system. These are shipped. Steel kind of copper, got all the bar in it, it's all designed, it's got this bearing beam in there. picking eyes. Typically what you do is you set these down in place, you wiggle them around, get them where you like them, you call up a concrete truck and fill them up. Then you'd wait 7 days, 4,000 PSI strength, 7 days. You know, here we didn't want to have to wait that extra 7 days. Also, just like the other steps, these were placed, then backfilled, and the old bridge was kept in service. So the county loaded these sills up on their flatbed, put a sheet of plastic down, drove over to the concrete plant, and had them fill them right up with concrete right there. Left the truck parked there for a week. Came back, picked the truck up, drove it up here. There's the sills ready to go. 1 day operation. Filled, set, ready to go, installed and backfilled. And then, like the other days, more geotech style gravel and compaction. Into day 4, on to day 5. Now it's time to remove and replace the deck. This was a big day. This was a long day. Everybody knew it was going to be a long day. Not quite sure how this existing bridge was going to come apart. There was a lot of ideas, a lot of suggestions. It was kind of interesting that when they reached down and nudged it with the excavator, it just came apart. So those old girders that you saw built up railroad beams or railroad cars or whatever they weren't even connected. Not bolted, not welded, not anything, just set down there and filled up with some concrete. They did pour some concrete in between the two pieces, but it didn't bond anything. Filled the space. So I think just picked them up with some chokers and there they went, out with the old. Got everything cleaned up. Now you see the facing, the existing walls, use the spacing, and then in with the new, right? Back the new bridge in, right on the truck. So here it is. Just like that, ready to go. Pick them up, set them. You kind of notice the bolt holes, how these are bolted together, even the intermediate diaphragm, right, bolts up. Everything's just a bolted connection. There's a minor amount of some welding that you'll see. One little note, just kind of a trick on these. Get some 4x8s, set them down on your sill, set the bridge on there. Instead of setting it right down on the sill, there is a bearing pad assembly that goes in between here, but it's a lot easier just to get everything set down, kind of in place. Then what you do is you do your fine adjustments, right? So here we are, we're going to just pick up this side, right? We've got everything lined up, all the bolt holes look great, diaphragms underneath, bolt holes look lined up great. Just going to pick this up, slide these blocks out and set it right down, and here's the bearing assembly that you see. So the plate, bearing pad, plate, and then once you set it down, you just weld that together, weld that to the bearing beam that's down here in the sill, bolt the center up, and here you are into day 5. So bridge is installed, 5 days, and you think about how many people you needed. Well, the county had 6 folks there, and I had to jump in the picture just because it's kind of cool to see something like this happen in 5 days. So there it is, bridge is in place. You kind of see the equipment that they got. All right, a couple excavators, small rollers, walk behind compactors. They didn't even bring the water truck up. They brought up a water tank and a sprayer, loader for packing the gravel around, dump truck for hauling off some of the excavation. Pretty simple equipment, stuff that I think most of all the counties and highway districts have. You don't need anything special. So construction day 6 is removal of the detour and kind of the final site cleanup. Like a good photographer, there wasn't a lot of pictures. but you kind of get the picture of the final cleanup and it's done, right? Removal of that stream crossing that went in through there. They had placed it down with chain link fence and filter fabric, and then the clean rock on top of that. So, you know, that theory of you just kind of pick all that chain link after you scrape off the rock you can, you pick up that chain link in the fabric and everything just pops back to how it was. So there's a couple of the final pictures, and then there's kind of a little comparison side by side. I think I had one more poll question besides how many days you thought it would take to replace it. That's in this poll question.
Okay, so we launched this one. How much did the bridge cost, not counting labor and equipment? What do you guys think? Less than 50, 75, 100, 150? So some mixed numbers here. What do you think, Matt?
Yeah, no, that's, you know, I'm glad to see people are tending towards the lower, because that's where it's at. You know, I think the county's going to end up right under 50. You know, the bridge itself and components was about 35. You know, you put in a little engineering, a little bit of fabric, and the concrete that they purchased. So, you know, we're not talking about labor and equipment, you know, fuel. You know, those items are kind of part of your road and bridge budget. They're part of your regular maintenance. You know, if they weren't replacing this bridge, they'd be out replacing some culverts, doing some ditching, maybe some brushing. So those are kind of costs that the county already has. So we rediverted those forces and those costs over to replacing the bridge. You know, right in that $50,000. This is to note, replaced with a 30-foot single lane, so it's 16-foot wide. You know, it's a single lane road. Single lane bridges all the way there. There's three other ones, two other ones just downstream and one more upstream. So, you know, the 16-foot wide bridge is plenty here. Turnouts on both sides. You know, there's kind of that in a nutshell. If there's any questions for me. You know, otherwise, you know, I'd like to just say, you know, thanks to LHTAC, FHWA for allowing, you know, HMH and Boundary County as well to be part of this process and kind of showcase this project and some of the other projects that Boundary County has done with the, you know, cost-effective bridge replacement process. So, thank you.
Thanks, Matt. That was a great presentation. Great example. Good project. So post-construction, after your bridge's construction, what's the next steps? Well, you need to notify ITD. Since ITD does keep the inventory for the bridges in the state, you do need to notify ITD and provide them with the plans and calculations for their records. You need to keep a record for yourself as well, but you do need to provide ITD with one. They will need to perform an initial inspection. I believe it's within 180 days of opening for a local bridge. They need to perform their initial inspection and load rating, and also get it scheduled for the routine inspection, whether that's 2 years or potentially 4 years. Also, you can't just build a bridge and forget it. It does need to be maintained. It's a big push here at LTAC recently too, is to start maintaining bridges better. You need to wash these bridges if they have concrete decks, clean drains, wash them, remove vegetation. For GRS-IBS in particular, fill any gaps in the wall facing, any blocks that may have been damaged or anything. And also monitor the erosion and SCOUR. Fix any of that as soon as you can. Couple of resources we have. We kind of compile all the resources we can onto our website. It's at the link above. If you go to our homepage at the T2 Center at the top, and then go down to the right side on GRS-IBS Innovative Bridge Construction, we'll take you to a list of resources, including the document on the right, which is a very good resource for the design and construction. I believe it was mentioned in that FHWA video. And I guess what we're getting to, it just like the old Geico commercial, it's so easy, even a caveman can do it. And the way I saw Matt's beard earlier this year, he pretty much looked like that. So just this is the final opportunity for any questions and hopefully potential answers if anybody has any. You can type them in or ask them out loud.
When you get a prefabricated bridge like what Matt was showing there, don't you have to have what kind of information do you have to give to ITD to load rate it?
Usually just the plans from the, like if it was Big R, True North, usually just the shop drawings that they produce are pretty sufficient. Yeah.
Yeah, I would kind of add that, you know, that's some of the increased efficiency. You know, we typically see with a regular design bid build, you know, to put something together that the contractor can bid, the bridge has to be designed, girders are designed, contractor bids it, they send it to the fabricator. They then come up with their own shop drawings. They want to change rebar, they want to change strand. So it's kind of this duplicated process. Through this process, we provide them a kind of a performance-driven spec. This is what we need. This is, you know, how tall we want the girders for clearance or other things, and they kind of figure it out. They figure out the engineering and they submit it that way. So it all comes from them, stamp, drawing, calculations, and we kind of tell them what you need to fit your location.
Any other questions? Well, great. Thanks everybody for participating. I think Amanda's going to give a plug for another training we're going to hold here in the near future.
Yeah, we did get a stick grant. We've been plugging it for a little while now. We've had to delay it. It was originally supposed to be last year. Because of COVID, we've had to delay it a few times because we really want part of the webinar to be in person, or not webinar, the workshop to be in person. So you can see some of these preservation and maintenance applications in person. But in the meantime, we have worked with a couple different groups to put on a webinar to do low cost maintenance to save bridges. It's very good. I've watched it before. The guy, Travis from ODOT, it's very applicable for local jurisdictions. It's free. We have the information on our T2 page. We've sent out emails. It's in our everything. It's everywhere. So if you're interested in that, please participate. It's, I think, an hour to 2 hours. And oh yeah, it's on there, hour and a half. And really well done. So please check out that while we continue to wait for it to be safe to have an in-person training, hopefully coming up.
Amanda, I did see there was one question from Art on the modular bridge system. So I think what he's saying is, you know, why not use I-beams? By all means, these modular bridge systems, when you get up and look at them, I mean, you could order your own, you could go to the steel supplier, get your own I-beams. You can order the deck pan separately. You could weld it together in your shop. I think when you add up that labor, welding, the increased engineering costs of designing your own I-beams and deck pans, you're going to see that these manufacturers are, you know, they're not making a fortune. They're probably, your inefficiencies and additional costs are where they're making their money, and they're streamlined, right? They've got the girders, they've got the ability to handle that steel. So by all means, you could build your own modular bridge superstructure out of steel and set it on your GRS-IBS system.
And along with that, yeah, I couldn't agree with you more, Matt. It's probably cheaper for them to do it themselves. But also, you know, I talked too about maybe potentially utilizing existing girders. If you have a bridge in your jurisdiction, you have some old steel girders, maybe you could utilize those in your new bridge, GRS-IBS bridge too.
Yeah, Scott was, I think, taken back a little bit when I sent him a Craigslist ad for some old bridge girders salvaged out of a Washington project. And so early on, you know, all those things, they're all viable until you kind of chase them out. So, yeah.
Don's going to finish us off here.
Yeah, I just want to follow up with a big thank you to everybody for participating today. We're going to process the recording, kind of clean it up. We'll take out some of our breaks and things like that, and then we'll send that link out to everybody in attendance today. Like I said, feel free to share it with those that weren't able to attend today. Also, the T2 Center will send out a follow-up survey. We really encourage your feedback, not only on this class presented today, but also other webinars and in-person training when we get to it that you'd like to see offered and that LHTAC can help with. So look for that in your email. And thank you everybody for attending.